Have you ever wanted to build an argument that's just completely bulletproof? So solid that nobody can poke a hole in it? Well, guess what? It's not some kind of superpower, it's a skill. And today, we're not going to get bogged down in a bunch of scary math. Nope, we're going to look at the simple, powerful rules for thinking clearly. Think of it like the source code for how we reason. Let's jump right in.
So yeah, how do we do it? How do you build that perfectly airtight argument? Well, today, we're going to build a whole system of reasoning right from scratch. We'll start with the tiniest little pieces and click them together step by step. Honestly, it's a lot like building with Legos.
And that most basic Lego block, the very first piece we need, in logic, we call it a proposition. You can think of it as an atom of truth. I'm not kidding, everything in logic starts right here. If you can get this one simple idea down, you're on your way to building some seriously powerful arguments.
Okay, so what in the world is a proposition? It's really simple. It's just a statement that is either true or false. That's it. There's no in-between, no kinda, no maybe. It's a completely black and white yes or no world. And this simple rule, it's the foundation for everything else we're going to build.
All right, let's look at some examples to make this super clear. On the left, you've got real propositions. Addis Ababa is the capital city of Ethiopia. That's true. We can verify that. 3 is an odd number. Also true. But now, look at the right side. These are not propositions. X is a city in Africa. Well, is it? We don't know. It totally depends on what X is. Same thing for X is greater than Y. Because their truth can change, they don't count.
Okay, so we've got our basic building blocks, our propositions. But, a pile of Legos is just a pile. Not very fun. You need a way to connect them, right? In logic, that's where connectives come in. They're basically the glue that lets us stick our propositions together to build bigger, way more interesting statements.
So our first type of glue is the word and. Logicians have a fancy name for it, a conjunction, but it's just and. And it works exactly like you'd think. It's a simple but really tough test. If you connect two statements with and, the whole thing is only true if both of the original pieces are true. Talk about a high standard, right?
And check out this truth table. It shows this perfectly. It lays out every single possibility. Just look down that P and Q column. See that? There's only one single T for true, and it only happens when both P and Q are true. Every other combo? False. No exceptions.
All right, let's get to our next connective. And this one is a big deal. It's the if-then statement. We call it an implication. This thing is the absolute heart of making a logical argument. It's how we form a hypothesis, how we talk about cause and effect. You could even say it's the engine of reasoning itself.
Okay, now this truth table might seem a little weird at first. I get it. An if P, then Q statement is only false in one very specific situation, when you start with something true and end up with something false. See that row? True, false, leads to false. The easiest way to think about it is like a promise. Let's say I promise you, if it rains, then I will bring an umbrella. The only way I break that promise is if it rains and I show up without my umbrella. If it doesn't rain, who cares if I have an umbrella or not? I didn't break my promise. A false start can't lead to a broken promise. That's why those last two rows are true.
So we keep coming back to these tables, right? And for a really good reason. It doesn't matter how complicated or insane our logical statements get, we have this one perfect, almost mechanical tool that lets us test it under every single possible scenario. And that amazing tool is the truth table.
You see, the real power of a truth table is that it covers everything. It maps out every single possibility, leaving no stone unturned. So with two propositions, P and Q, you have 4 possible combos. But what if you add a third one, say R? Well, now you've jumped to 8 rows. It just goes to show how fast things can get complex, but also that we have a system ready to handle it.
And you know what? Building one of these isn't some kind of dark art. It's really just like following a recipe. First, you list your basic ingredients, your propositions, P and Q. Then, you make columns for each little part of the statement. You always work from the inside out, just like you would in math. And then, at the end, you figure out the final answer for the whole thing. It's a really clean, systematic process.
Okay, let's take stock. We've got our building blocks, we've got our glue, we even have a tool to test everything we build, so I think it's time for the main event. Let's build what we came here to build, a real, formal, valid argument.
So at its core, any formal argument is all about structure. You start with a few statements, which we call premises. And these premises are supposed to lead you to another statement, which we call the conclusion. And you'll often see this little symbol with 3 dots in a triangle. That just means therefore. It's the big signpost that says, hey, here comes the conclusion.
Okay, lean in because this next part is maybe the most important concept of all. An argument is called valid if its structure is solid. It doesn't actually matter if the conclusion is true in real life. A valid argument is basically a promise. It says, if your starting points, your premises, are true, then the conclusion has to be true. It's all about that logical link, not whether the facts themselves are right.
Let's try this out with an example that we can all understand. Here's the argument. If it rains, the crops will be good. It did not rain, therefore the crops were not good. I mean, that sounds pretty reasonable, doesn't it? It feels like common sense. But the real question is it logically valid?
First things first, let's translate this from English into our logic speak. So premise 1 is, if it rains, we'll call that P, then the crops will be good. We'll call that Q. So that's P implies Q. Premise 2, it did not rain. That's just the opposite of P, or not P. And the conclusion, therefore the crops were not good, which is not Q.
So, the million-dollar question, is this argument valid? Let's put it to the test. Remember the rule. An argument is invalid if you can find even one scenario where the premises are true but the conclusion is false. So let's imagine a world where it didn't rain, so P is false, but the crops were great anyway. Maybe they had a new irrigation system, right? So Q is true. Now let's check our premises. Premise 1, if it rains, then crops are good. Is that true in our world? Yes, remember the truth table? When the if part is false, the whole if-then statement is true. Premise 2, it did not rain. That's also true in our little story. So we have 2 true premises. But what about our conclusion? The crops were not good. That's false. And there it is. We found a situation where we have true premises and a false conclusion. That means the argument is invalid.
And that right there is the power of all this. We just built a system from the ground up that can test the very structure of an argument. So here's my question for you. Now that you have these tools, how many of those common sense arguments you hear every single day are actually built on a totally flawed, invalid foundation? I bet you'll start seeing them everywhere.